My name is Ron Bonica, and many years ago when I first started working as a network engineer, I remember debugging, many times debugging network problems with ping and traceroute. And my boss used to say, ping and traceroute are your friends. Well, yes, they are my friends, but there are some nuances of ping and traceroute that we need to understand and even address some of its shortcomings. And that's what we're going to talk about today. Ping is very good at determining the status of a reachable interface. That is, an interface that has an address, a globally reachable address, and that you can reach. It's not very good at determining the status of unreachable interfaces, say unnumbered interfaces or interfaces that you don't have a route to. Traceroute is very good about telling you what nodes you visit along the packet's delivery path, but it's not very good at telling you what interfaces you visited. So, back a few years ago, we did some work on each of them. One was called Probe, RFC 8335. The other was called Extensions to ICMP for Unnumbered Interfaces. That's RFC 5387. We did that work, we integrated it into Junos, and then we found that it was a great thing to have in Junos, but it really wasn't very useful unless there was support for it in Linux, and Wireshark, and TCP dump. So, a group of students from Harvey Mudd University, listed here, Ishan, Andreas, Spencer, and Nick, developed support for these two RFCs in a few open source projects, Linux, Wireshark, TCP dump. The mentors were myself and Zach Dodd. In any event, since the students from Harvey Mudd did most of the work, I'm going to hand it over to Andreas and let him talk about exactly what the team did. Andreas?
Awesome. Thank you, Ron. So as Ron just said, we're going to be talking about ping and traceroute, which are the most commonly used tools in the IP OAM toolkit. However, as we'll see in this presentation, they have some limitations and cannot always provide us the information about a network that we might want. Specifically, there are many instances where these tools can only provide us information at the node level and not at the interface level, where the node level is a node is something like a router or a host on a network that communicates to other nodes through its interfaces. So for the rest of this presentation, we're going to look at ping and traceroute and follow the structure outlined here, where we're going to examine what they do, how they work, what they can't do, and how we've been working to enhance them this year. So starting off with ping. So ping tests the liveliness of a reachable interface, and it does this by sending a message to the address that identifies that interface. And by proxy, you can test the liveliness of a reachable node, and you do this by sending a message to one of its reachable interfaces, and when you get a message back, you will then know that the node is up. And ping does this by your probing node, so your host, the one where you are sending the message, will send an ICMP echo to a probed interface. And that's the interface you're trying to learn about that lies on a proxy node. And then the probed interface, or the proxy node, will send an ICMP echo reply back to you, the probing node. And in the nerd notes section, we're going to get a bit more technical, and we can see with this command that if we want to learn about a specific interface on a node and determine if that interface is up, we can run into problems with the current ping command, because the ICMP echo may enter the probe node through any of its interfaces, and we might not know which one it enters through. And similarly, it can leave the probe node through any of its interfaces. And there's no guarantee that either ICMP message traverses the probed interface we would like to learn more about. So what can't it do? It can't test the liveliness of a less than reachable interface. And an example of this would be something like an IPv4 unnumbered interface, which are becoming a lot more popular. And since they don't specifically have their own IP address, you can't ping them directly, and you couldn't learn of their status using the current tools. Similarly, IPv6 unicast with narrowly scoped addresses or any interface to which the probing node lacks a route cannot be queried with the conventional ping command. And this often has a lot of information that we might want to know about. So in order to enhance this, RFC 8335 was published. And what this RFC describes is an extension tacked on to the existing ICMP echo messages. And using this command, a probing node will send an ICMP extended echo request to a proxy interface. And the echo request identifies the probed interface that you would like to learn more information about. And the proxy interface then reads this identifier and responds with an ICMP extended echo, which tells us information about the probe node. Thus, we can get a more specific information about the interface on a node, and we can learn more about interfaces that we couldn't otherwise query. So let's quickly look at a diagram of this in action. In this example, my colleague Nick would like to learn about interface 3 that is on this proxy node. However, for whatever reason, his messages are only getting to interface 2 on the proxy node. This could be because the network topology happens to direct his messages there. It could be that interface 3 is unnumbered, and therefore it's impossible to directly query it. And if you were using ping, there would be no more information that you could actually gather at this point. You would know that the node itself is up, but we would have no idea how interface 3 is doing, what its status is. But using probe, you can specifically ask, how is interface 3? And even though your messages are still only getting to interface 2 on the proxy node, it will respond with the information telling you interface 3 is up. So therefore, you can learn about interface 3 without directly having access to that, without your message directly going to that interface. So from a more technical standpoint, the proxy interface for proxy interface in general can be different than the probed interface, the interface that you would like to know more about. And in many cases, it is different. So similar to ping, probe needs to have a connection to, the proxy interface must be reachable from the probing node, but probe also allows you to cast a wider net essentially and gather more information, because the proxy interface that you're trying to query may reside on the same node as the probed interface, or it could be a node that is directly connected to the probed interface. You kind of expand your range with probe as well. So not only do you get more specified information, you can also gather more information about nodes that are more difficult to reach. So let's look at what this might look like if you were to use this command. So this is a terminal output that might look familiar to many of you, where we're using the ping command. However, in the command line at the very top, we see this -E, and that is the functionality that we have added this year, and that specifies we're using the extension structure. And in this case, we pass the name of an interface, in this case, GE-000, to the extension structure. And that interface is an interface that lies either on or is one hop away from the IP address specified starting with 10. And we get a normal output. You still get your time, your latency and everything. But in the bottom right, we now also have this additional field that tells us the status. And this isn't the status of the node, which is all ping can tell us. This is the status of the interface GE000. And this is telling us that it is active and responding to both IPv4 and IPv6. So we get a lot more information. And in this instance, we don't necessarily know if our messages are getting directly to that interface, but we can still gather information about it. So that is very useful. Now, as with any time you give information about your network, there are a couple security considerations that might be alarming. We're giving a lot of information, not just about the topology, but about specific interfaces inside of our network. So to address these concerns, we really have two approaches. So first, every implementation does not enable responding to probe messages by default. And this allows you to, when you have an error that you're trying to debug, you can enable it, query your own network, and then disable it. So anyone else at any other time will not be able to gather this information about your network, and only you can because you have that control. As a fancier option, you can also specify it that nodes will only respond to probe commands from specified source addresses. So you can have your list of approved IP addresses or approved sets of IP addresses. And when these nodes query your hosts, then they will reply with the full probed information that we have been talking about. But other nodes can, if it is an unrecognized source address, the node can either respond with a generic ping request, as it might now, or it could just drop the message entirely. So these are the things we have done to try to address these issues. Now, there's a good amount of support for probe as of right now. So Juniper, in its Junos 20.3 R1 line, which is currently deployed, completely supports probe functionality and is up. Similarly, the Linux kernel has just gotten approved probe functionality in 5.13, so that will be rolling out very soon. And the IPutils package, which is installed on top of Linux and is the one that actually sends the message. The kernel is just the one that responds to requests. The maintainers of that package are currently reviewing our work, and hopefully that will be accepted soon. In terms of dissectors and other tools, Wireshark version 3.5 or newer can completely dissect and parse probe packets, both replies and requests. And TCP dump, the maintainers, similarly to the IPutils package, are currently reviewing our work. So that is a brief look at probe, and now we're going to switch gears to traceroute. So this is going to have the same structure to what we just went through with probe. We're going to talk about what traceroute does, how it works, what its limitations are, and what we've been doing to address these issues. So to begin with, traceroute elicits feedback from each node along a delivery path between a probing interface and a destination interface. So again, it only gives you information at the node level. It can only identify the nodes along the delivery path. And this tool is commonly used to try to learn what path our messages are taking through a network to try to determine issues that way. So traceroute works when your probing node, your machine, sends a series of UDP packets to a destination interface, and it sets the time to live, or TTL, to 1 on the first packet. And when that packet gets to the first node along the delivery path, that message will expire, and that node, the first node along the path, will respond with an ICMP time expired message. And that is how we gather information about the delivery path. On the next iteration of the command, it will increment the time to live so that it expires on the second node, and then the third, and so on until we reach our destination. So to get a bit more technical, for the UDP probe messages that your machine sends, by default, the probing node sets the UDP destination port to 33434 and increments that destination port on each subsequent packet. For the ICMP time expired message that the node on the delivery path sends back to us, the source address that we get back might not identify the interface upon which the UDP probe message arrived. So it might not be telling us what interface our messages are getting to. Instead, it will only tell us an interface on the node that is responding back to us, which is a bit less useful, and we might want to know exactly where our messages are going, not just the nodes, but the interface. So for IPv4, the source address that we get back identifies the interface through which the ICMP message left the reporting node. So again, it identifies an interface on the node, but not necessarily one that our message is arriving at. And for IPv6, there can be any node, there can be a wide range of responses, and we don't necessarily know which one it is. For more information, what it can respond with is defined in RFC 6724. So what traceroute can't do is it can't identify the interfaces along the delivery path, only the nodes. And in order to enhance this, RFC 5837 has been published, and it tries to add an extension to the ICMP time expired message that gives us interface level information about it. And the great news about this specific command is that the UDP probe message that we're sending out is actually unchanged. We don't need to do anything to it. The only thing that changes is the response message that is generated at the node on the delivery path. So the ICMP time expired message can contain this extension defined in RFC 5837 that identifies the interface upon which the UDP probe message arrived. So that's where we're actually reaching with our messages, which is the most important thing when we're trying to determine traceroute or the delivery path. And it can also tell us the interface through which the message would have been routed had the time to live not expired. So this is not only telling us where our messages are arriving, but also where they would go in the next hop, which is very useful. And the things that can tell us about those interfaces are the name, the IP address, and the maximum transmission unit. So let's look at an example terminal output of what it might look like to use this. So here we have a traceroute output that might look very familiar, where we have 12 hops on our delivery path. But now we're adding these sections in the blue boxes. So let's zoom into the example number 5 on the list. So here we see that the node that responded to us has an IPv4 address that begins with 68. And if we were using regular traceroute without the 5837 extension, this is all the information that we would receive. However, with this extension, we get this additional printout that tells us our arrival interface is an interface with the name EN2 on the node, and its address actually begins with a 38. So it's a very different IP address than the one that is getting back to us. So we can get a lot more fine-grained information, and we can learn where our messages are actually arriving on the nodes along the delivery path, not just an IP address of an interface associated with that node. Now, similar to probe, this command can have a lot of security considerations because, once again, we are giving information about the network out. So in order to address these, we take the exact same steps that we did with probe. So first, we do not enable this by default. The default behavior is the same as the default traceroute behavior, which can also be disabled. And you can set it up so that it replies with this extra interface information only with verified source addresses that are on a list. And for everyone else, it can either just drop the request or respond with a generic traceroute message that you might receive today. For implementations, there are a lot in progress. It is not as deployed as the probe command is, but there are many places where it is being worked on. So for Juniper, in the Junos line, they are currently working on it, and it will be deployed starting with the EX series of routers first. The Linux kernel maintainers are currently reviewing our code and evaluating it to see if they would like to accept it into the Linux kernel. But the code itself is finished, so it's more in the process of being accepted. And same thing for the IPutils package in Linux. The code has been submitted and is currently under review. And Wireshark, starting with version 3.5 and newer, can completely dissect and parse the RFC 5837 extensions, and that is currently up in the version of Wireshark. So that has been our presentation. Thank you for listening, and we're now opening the floor to any questions.
Thank you, Ron and Andreas, for that wonderful presentation. We've got a few questions for you, and I believe that you both have the Q&A tab up. And our first question comes from Matthew Peacock. Would one of you be able to answer that?
Hang on just a second so I can see the whole question. All I see is a reference to an internet draft from Matthew.
Okay, well, it is when specifying the interface name, are you going to give the DNS name of the interface, or is that the internal interface name as determined by the device being probed itself?
The latter.
That is the latter, okay.
Yes.
And then Matthew also asks again, for traceroute, when you say the interface packet would have been routed out had the time to live not expired, is that doing a simple RIB lookup, or does it do a layer 2 hash calculation as well as when the outgoing interface is an aggregated interface, i.e., is it RIB only lookup or RIB to FIB lookup?
RIB only.
RIB only. Excellent. Matthew, hopefully that was good for you. The next question is from Tony Talbert. Seeing that extra info in the trace route makes me yearn for more well-structured output, e.g. JOSN. Any work in that vein, or is it a client program issue?
You know, Tony, I've never thought of that before. Just because ICMP messages are structured the way they were since 1976, I just went on in that vein. I never thought about a JSON output, but that actually is a really good idea.
But I feel like on the side of traceroute, the command, that would be handled by the program and not in the ICMP message. Like the parser for that would just format it as a JSON and then output it that way. And that would not be on the command function.
Any more questions out there?
Tony brings up a really good point, though. Many of the basic protocols in the internet were designed the way they were as a matter of history. You know, we needed to save bytes back in the days when the network ran on T1s. Now, JSON really wouldn't be a bad idea.
Are they completely opposed to having
Michael Doherty says, nice presentation and very interesting. Tony responds, also given the interface specification is dependent on the device, do you give an error if that's incorrect?
I'm sorry, I'm not quite sure I understood the question.
I'll repeat it. Also given that the interface specification is dependent on the device, do you give an error if that is incorrect?
Okay, I get it. Let's say you ask for GE-0-0-, but on this device it's GE0/0/0. The error you will get back is that there is no such interface. If one character in the interface name is wrong, there's no such interface.
Okay. Kevin McCormick has just asked, could you have a command option to output as JOSN? JSON.
Yeah, that would actually be easy. You get the ICMP message back, and rather than putting it out as, the text that Ping and TRACEROUTE put out today, well, why not put it out as JSON? That's actually a really good idea. I wish we'd talked to you guys before we did the work.
Matthew Peacock asks again, are interface names case sensitive?
I believe they are. Andreas, you did the work, are they?
So the way that it's handled in Linux is it just uses the default lookup for Linux interfaces. So it would depend on that functionality. So I off the top of my head, I don't know if it's case specific. We can test that.
James Martin comments, great presentation, Andreas.
No, thanks.
All right. Well, we have 4 minutes left to our next presentation. If we don't have any other comments or questions, we're going to pause for a brief moment until 12:30 when we resume our next presentation. Let me see if we have anything else. Once again, I'd like to thank Andreas and Ron for presenting at today's second day of NANOG 82. We are going to take just got something in from Tony again. Right, the interface naming is not something that usually known without specific inside knowledge SNMP queries can give you, but they are usually not available from outside the operator. So it looks like that's a comment, not a question. So excellent.